Hello and welcome back to our conversation with Aston Photonics. I'm Brian Sudlow. I'm joined again by Professor Andrew Ellis.
Hello.
By Professor Wladek Forysiak.
Hello.
And by Dr. Ilaria Scaglia.
Hello.
So we were just chatting about some of the problems behind this wonderful revolution in photonic technologies, which underpins the digital world in which we're living. And I think it might be worth digging into some of these issues from an engineering perspective, but also then from a historical perspective as well, because this isn't our first rodeo. We've met technical crises before, and problems hopefully can be found. But Wladek and Andrew, back to you. What are the challenges that lie there, perhaps below the surface, or perhaps not so much below the surface these days?
Oh, good question. Well, one of the big challenges Andrew already mentioned, which is about our expectation, I think, as a society to be able to communicate at will from any place, and to be able to transport more and more data. And that's driven by our consumption of data, which is not in simple, easy form, in the form of the written word, but rather increasingly the spoken word, the sung word, and indeed in video form, and who knows what might be in the future in terms of gaming requirements and so on. So the challenge is that we have a finite amount of money that any of us as individuals want to spend on our communications, yet we want to have much more for that finite amount of money. So the challenge of it for us as technicians, or as researchers and as technologists, is to try to provide that ever increasing demand for data consumption in whatever form it may be.
Now, this might not be the right question, but actually, can such a demand be met? Can we quantify that demand? Do we have the resources to meet demand? I mean, demands need resources to be met. So are we able to do that?
Well, again, Andrew talked about it last time, that for 10 years or longer, we've had this potential for the capacity crunch and the ever increasing demand on energy that's associated with processing the data, sending it, receiving it, and so on. One way that we've been able to historically deal with this, or at least mitigate the demands, is that the great advances that have been made in very large-scale integration in computer chips, making the feature sizes ever smaller, and therefore making those gates function with decreasing the amount of energy. And we've been able to introduce new generations of those chips in a sufficiently speedy way to help mitigate those demands. So you'll have heard of Moore's law. Moore's law is this classic doubling of capability over an 18-month period. Now, this is possibly slowing down more recently, or becoming more challenging, but it's incredible the innovative capacity of man to look for different types of solutions here, whether through parallelism or whatever. Maybe Andrew can comment on this.
Indeed, and we see a very similar exponential growth in the communications. That it goes back 400 years. So perhaps Moore's law's a bit of a recent name for this exponential growth. The thing with exponential growth is no matter how big the petri dish that you're growing your cells in, or how large the field that the rabbits are growing in, they'll grow exponentially until they hit the boundary. And what's going to happen when you hit the boundary? Well, one thing you can do is you can open the gate and do another field. But now you have to maintain two fields. And so the conversation should be about, do we have some way of containing the population, constraining the bandwidth that people use to what we're able to deliver for that fixed amount of money? Or do we want to pay more money for unlimited service? That's the conversation I think the society needs to have rather than the technologists. I think it's our job to highlight that we're getting to the point where the petri dishes are looking full, where the rabbits are starting to overrun the field, where the fibers are getting full. What does society want us to do?
What does society want us to do? So this is a problem of means and ends, isn't it? in fact, I think Imperial College London has a does it not have a project, a course called Means and Ends, where precisely the technologists and engineers are brought into that conversation, not only about the technical means, but in fact about which ends society wants to benefit from. Of course, there's always costs to these things, though, aren't there? I think one thing that I'd like to point out as well, in addition to this capacity issue, is there not also a materials issue as well? Is it not the case that a lot of digital technologies ultimately need to draw on extractive industries that use elements, metals, and so on, which are themselves finite in nature, so that even if one could increase the capacity for the data capacity and so on, is there not behind that data crunch issue also just a sheer material resource issue as well?
That's one of the really great things about optical fiber. That it's made of silica, which is kind of like sand. Very, very, very pure sand that's processed very, very well. And even better than that, I think Wladek mentioned it earlier on, there's a new British fiber come along that's hollow in the middle. Not only is that great because it's low loss and low latency, so you can get the information there quickly, it doesn't matter how pure. Well, it does matter to a certain extent, but it matters less how pure that is. So we need to purify that sand even less than we did before to get good results with this new fiber. So as far as the actual fiber is concerned, I think we've got a good story that we've got plenty of resource available without really deep mining to get hold of those minerals.
Yeah.
When it comes to your phones and your computers, then you are using some precious metals, and certainly batteries. There's a lot of controversy at the moment about extraction of materials from batteries. So the devices we have at the end, yes, I think there's a problem on mineral extraction for us to talk about. For the actual communication link itself, it's in the air, that's not using anything, and it's in an optical fiber, and that's very plentiful.
And that's a very interesting point about the silicon. But there's also in a different way a material issue when it comes to the running of the data centers. You said Dublin had banned the running of new data centers. This has an ecological dimension to it as well, doesn't it?
Indeed, it does. The Colorado River apparently is running quite low these days because of all the water that's extracted for cooling. Google have a project on nuclear-powered data centers. Dublin has run out. So there is an energy problem with data centers at the moment. A big European one is in Amsterdam, where they have lots of hydropower. They like data centers in Ireland and Norway because it's easier cooling with the natural resources available there. So this energy consumption issue is a big thing. Currently in the data center, it was in the network, and it's certainly in people's devices.
Yeah. Ilaria, is there a historical approach to the kind of issues that we're talking about here? You know, we started with the capacity crunch. We've been thinking about materials. We've been thinking about ecology. What's the historian's perspective on these?
Well, the Industrial Revolution, of which many of the technologies in communications were part of, at a tremendous cost from an environmental standpoint and also from a monetary standpoint. You know, people's money resources were used to do that. They maybe could have been used to do something else, to build houses, for healthcare or for other needs. So that's certainly a lesson that we might want to keep in mind. And it's a bewildering one because already historically people were often thinking about the capacity crunch in other ways, right? But they were thinking, how many cables can we really fit under the ocean? How many of these can we possibly make? But often they answer that question without worrying about what that would mean. The famous case is gutta percha, right? So this vegetable,
perhaps you could explain that
this plant that was used. I'm not an expert in medicinal any stretch, but I understand it's a plant that was used because Then a substance could be extracted from it to make cables watertight, I think, or more resilient.
It was almost like a kind of latex.
It was like a kind of latex.
Coat the cables. Yeah.
The revolution, the telegraphic revolution, led to the extinction of this very plant. So people just kept worrying about, how many of these can we make without ever thinking about, okay, but now you're not able to purchase. And what does that mean? What does it mean from an environmental standpoint? And often when we worry about, say, the capacity crunch, we think about, okay, how many of these things we can make with the resources we have, and then we can use more resources. But, historically, people, asked the question of, what does it mean then? Now you have a big mine. Now you have people that for 2 generations, 3 generations mine this particular area, and now the metal is gone, it's finished. What's going to happen to them? What does it mean environmentally? Can you still cultivate this area now? Can you still do something with it or not? These kind of questions historically have not been asked. While these technologies were being developed, were only asked after the damage had been done. So most of the environmental damage was done during the 19th century, during the Industrial Revolution. And that's, I think, a useful thing to remember. The other point that might be helpful is about the democratizing promise of this technology. The telegraph was never free at the point of use. It was never free to send a telegraph. But so people were mindful. They wouldn't just telegraph lightly because they knew they had to pay. But it was affordable. People did send a lot of telegraphs. And it wasn't only wealthy people that did that. The particularity about the digital thing is that it's free at the point of use. Apparently, I can take my phone and just snap away, and those pictures are free. They're not like the old film, pictures on film I would have to pay to get developed. And this gives this illusion of something being free and something being democratic. Everybody can do it. And so it becomes a bit sneaky then, because then it turns out it's not quite free, right? It consumes electricity to sustain this whole process. It consumes resources to sustain this whole process. Increasingly, we have areas, I understand, that are served better than others when it comes to those cables and how quickly you can transmit the data. And so a big question historically then to ask is about how much the promise of democratization was fulfilled or not. Did it really happen that the new technology put everybody on the same plane, or did it not? And historically didn't quite. Human beings seem to always find a way to stratify and to create levels and to have somebody at the top that either access more or accesses better, either out of, again, something being faster or something being more capacious, or something just being cooler, being a more charming status symbol than to show off in front of others. But historically, that's what human beings tended to do. They tended to stratify it. So I guess one of the thoughts that comes to mind listening to this very engaging conversation is, what is happening now? Is the free picture free for everyone the same way? And do we see any sign of a hierarchy being created? Are some cables better than others? Are some areas better served than others? Just looking at the map, for some reason, I cannot help but notice, some areas with lots of colors and some without.
Some areas are definitely better served than others. We've been involved in a project in South Africa looking at bringing what they call sustainable photonics to Africa to bring broadband to everybody. What they mean by sustainable is that Africa makes its own equipment. It doesn't buy stuff from America or from Scandinavia or from China or Japan. It manufactures its own solutions. I'm trying to address exactly that digital divide that we have across the world, that some people are able to take free photographs. Other people would struggle to get hold of a camera.
So there's that question of technology bringing change is let's say very, very conditional. In fact, it very much depends upon the circumstances, very much depends upon the environment and so on. I think we're getting in that in the question of the unequal distribution, the question of democratization. I think we're getting to something that is very deeply embedded in the history of technology, which is that technology is always a double-edged sword. We almost always embrace it because of the one edge, which is the cutting edge that we want. and that brings the undoubted benefits, that's making possible just our very conversation here, which otherwise might be just a conversation between four people and lost forever, and now it's preserved and it will be distributed, and perhaps other people will listen to it and so on. We can think about all the commercial benefits. We can think about the health benefits, I think, that are now being seen within that field, that developing field of digital health and so on. But then there's this, as I say, and we see it again and again in the history of technology, there's always the other edge. There's always the hidden costs. And I suppose one of the things it seems to me that the history of technology teaches about hidden costs is that we have to strive to quantify these things, because what we don't want are the unintended consequences. And it's the unintended consequences which if we don't have a better sense of those unintended consequences, we could be in trouble. It's too late for the gutta percha, but there could well be other costs, other hidden costs that we're not aware of. People always laugh when I quote Donald Rumsfeld in my course on social action. But Donald Rumsfeld famously spoke apparent gibberish that was actually extremely lucid. This was, I'm going back now a couple of decades. There are the known knowns, the things we know. There are the known unknowns, the things we know we don't know. But there are also the unknown unknowns. What's around the corner that we haven't even got a sense is there. Now, I'm not being alarmist, because what I'm saying is that this is what history of technology teaches us. It's often the unexpected that catches us out. In our next conversation, we will be talking about solutions. We will be talking about positive ways forward. But just for a minute or two now, indulge me. What's the worst that can happen because of this capacity crunch? What's the worst that can happen because of these material problems as well, or the problems of uneven distribution and so on that we've been evoking?
Well, I don't know what's the worst that can happen, but certainly something that I see on the horizon that will be a challenge is that the way that technology has dealt with the issue of coping with the energy requirements, adding the data capacity and meeting the data capacity demands, that's changing, or that is going to be challenged. So the solutions that we have for delivering data from one end of a fiber to another depend on very complex chips at each end, in the transmitter and in the receiver. And there's a process known as digital signal processing, which helps to clean up the signal so that you receive the signal that's indeed been transmitted. The development costs of those so-called DSP chips are rising every time the feature sizes associated with the semiconductors required come down, and we need increasingly more and more of those processes or more gates on those chips because of the complexity and the increasing speed. Now, I was talking to a leading industrialist yesterday, just on a call on an external advisory board, and he was reflecting that the last generation of such chips, 7 or 8 companies had the resources to develop those chips. For the next generation, he's seeing perhaps 2, perhaps 3. Now, that's not the way that commerce, business, capitalism works well, I think, for the consumer. If we're down to 2 or 3 suppliers, only 2 or 3 suppliers being potentially able to develop those chips as we go forward, we've got a potential problem on our hands.
And that's not just an economic or a manufacturing problem, that's a political problem as well.
In addition, absolutely, yes. I'm focusing on the economic aspect, but yes, indeed.
Yeah. Andrew, how do you see this?
Well, on a similar vein, Wladek's talked about how you could end up with a small number of players controlling what people see as a key resource. From the position that I'm looking at, the worst that could happen is that we can no longer grow the capacity, but that people want more use. And you will get a tension between government saying, no, connected ambulance is much more important than skateboarding cat, and passing legislation where net neutrality is gone, that some applications are more important than others. And whilst with the current people, I'm confident that that won't lead to anything bad. Looking at history, I'm not confident that that will always be the case. And once you cross that Rubicon of saying that some applications are more important than others, you can get disasters. The other worst thing that could happen, of course, is that communication technology has always been, you referenced the Crimea, it's always been dual use. So that's another worst case that could happen.
So, Ilaria, what's your take on this?
Well, I often think to myself and tell my students that there are more continuities than breaks in history. Mm-hmm. Often we find patterns repeated, rather than this turning point with nothing to do beforehand. And sometimes these are good, right? Aston had a long tradition in optometry. I understand most optometrists in the UK were trained at Aston. And as that, then there was a development for optics that then matured into photonics, right? So sometimes continuity is good, but sometimes continuities can be troubling. So when I look at those maps, what I see are actually two very similar maps, connecting empire with colonies. And historically, the people who really paid the greatest price when it came to the environmental cost, when it came to all sorts of different dynamics that developed from the unrestrained development of new technologies, happened to be in areas that either were colonies where they were working for nothing, sometimes enslaved, or they were taken advantage of, entire areas used as dumping grounds, mining grounds, no questions asked. And what concerned me when I look at those maps and when I keep in mind those continuities is that the pattern might continue. In the end, the usual suspects are going to be the ones who are not connected, who are exploited for the materials, are exploited for their territories and everything else. And in addition to that, because of the dynamics that were just described, are going to be kept out of the center of power that then decides which company controls the chip, who decides in the end what you see when you check the news or you see the results on your little internet search. They're going to be left out of that as they were historically. And that cannot end well. We already see the results of colonialism in the form of tensions, international, nationally, and so on. This can only get worse when it comes to now this mass implementation of digital things, unless we don't do this sustainably, ethically, recognizing some of the troublesome continuities and trying to mitigate.
Thank you very much indeed. So hopefully we're not depressed, the listeners there, but okay, we've looked over the edge of the abyss. We might still evoke some of these issues, but in our next conversation, perhaps we'll also come to thinking about positive steps forward and the right technical solutions, but also maybe considering some of the wider cultural and political ones as well. For now, thank you very much indeed.
Well, thank you.
Thank you.
Thank you.